I'm just going to ask a couple of very gently, just initially. So I guess the first thing I'd be interested to know, which is one of the things I always ask with a thesis, is what was the actual background to the development of the project? Clearly, in one sense, it's been going on for a long time. So how did you all sort of involved, and how did you end up sort of focusing on this?
So as I did a PhD, there have been actually a long time since people looked at this data. So what I did is I started again from scratch. So what I did is I tried to redo Gauter's work and then tried to go further. There have been actually quite some problems at the beginning, trying to figure out, what are they measuring? Also, there have been some problems. Sometimes records have been switched on the wires, for example, so the raw data. There's been some work on there. And then what happened is I saw a figure from Gauter's work, which showed that sometimes these 6, 7 sensors were showing the same variation. And then I thought, that's showing connectivity. That's showing something important. Then it is, because it tells us that we can, maybe the glacier at some point respond to the water and it slides homogeneously. So there is maybe this idea that there is something general happening. So maybe I could try to extrapolate what we observe, try to look at the data behind. And so I started this this correlation stuff. But yeah, that's how we came up. Then I didn't start my PhD with that. I had all this data, but it's always fun to start with not the archive, not what we have under the table and kind of dusty. So I started doing this mapping that I didn't mention, using the Kinect, so this 3D laser scanner. And then I also worked with this, it was a new technology at the time, structure for motion. So it's like you take pictures, and from pictures you can observe a 3D model. But what happened is I quickly got stuck with that. At the times, the tools were not available. So then I switched back to this data, pressure data. That's approximately how it went. And then as you observe more in this data, so this anti-correlation, I was like, what the fuck, what's happening? It was really surprising. Then I figured out, okay, we need a process. And then I looked at all the papers and tried to reproduce what they were doing. So this load transfer, there is this Murray and Clark 1996 paper, and I tried to say, okay, can we investigate it? Can we reproduce what we observe? And then we have these events. It's like something that I think is it's happening a lot. So it's telling us that there is a process coming again and again. And then I thought, okay, let's try first to pick these events and then do this statistical analysis, maybe understand more. And then I had these 1,000 events, so I could try to do this PCA, the principal component analysis, trying to find what is the general shape. This closure came a bit in between, because we had some field work. And then Gauter had a problem publishing one of his paper, which looked at so what we call stress bridging. So it's like the bridge thing. So you had the bridge, and you had this increase in pressure. And we observed that sometimes it's as if there is 2 glaciers stacking on top of each other. So instead of measuring 1 megapascal, we measure 2. And so I tried to start again and reproduce this model, and then go a bit further, because I think, the paper was rejected because there was no, they didn't believe in the data. So we thought, okay, let's reproduce this data by melting a cavity and letting it close. So that went in between, but all the chapters, all the processing, everything was done before, between February and November.
More detailed questions, whereas people in some parts go into very detail, that I understand. And some will ask that you can step a bit out of the cavern and see a bit one is you told me that your grandparents are at the other end.
Yes, yes, yes.
So I guess they're total experts in basic sliding now.
They must.
Maybe not their friends
Yes.
in the village. So if you, when you go home after you have passed this ordeal here, and meet the friends of your grandparents in town, and they ask you, well, Tim, but what is it you've done in your thesis? It looked complicated. How would you explain your work to a non-academic in a few sentences?
I try to understand how does the ice move, and we know the ice is reacting to the melt. So we have the melt at the surface, and this water goes to the bed, and there actually the water has problem flowing. So you have a very strong increase in water pressure, and this can lift up the ice, make it slide. And that's what I'm looking at this interaction. And one way we looked at it is to look at the spatial variation. So how does it propagate? We have this lateral aspect, and that's the beauty of this network. Then I sometimes mention that I work in this the most claustrophobic lab in the world. But that's how I would summarize to someone.
Okay, and my follow-up question, Pete already put a lot of it on his slides, but then this person would ask, but I'm living in the middle of France. What does it mean to me? What is the impact of your work for my daily life?
Yeah. So what's the lucky thing is I come from a place which is rather low. So we are expecting to have some beach, nice coast environment. When my father thinks about buying a house, he always think, okay, 6 meters above the current sea level. We just have to wait a bit, and we'll have a sea closer. So what I mentioned to them is, I mentioned this relationship with how does the ice flow, and this, if the ice, so the glaciers, they bring fresh water. So this water from the continents to the sea. And if you bring this water to the sea, you increase sea level rise. And that's the most important thing, that it can affect large areas. And the thing is, we don't look at small glaciers, like Gabriel. We look at Greenland, that is showing very, very strong changes. We look at Antarctica, and then we see that actually their mass is increasing. They are bringing more and more water to the sea, and sea level is rising faster and faster. So in a couple of hundreds, thousands of years, you may have actually a beach on your feet. Where I come from, so Rennes.
Yeah, thank you. So the next question is starting a bit more detailed, and we are also going back from town into a classroom.
Hmm?
I guess it could be that you become a lecturer after your thesis, who knows? Now you have the glaciology students in the first degree, and actually heard a lot of details now, but actually what are the main factors controlling this glacier sliding at the glacier bed?
It's water pressure. But to look at water pressure, you need to look at two things. Again, so the melt, you need water. It needs to come from somewhere. So you need to assess the melt, and then you need to see, so how does this water flow? Because if it does not flow well, you increase the water pressure. That's what Pete mentioned. And if it flows very well, then you decrease the water pressure. So that's the key point. Obviously, I'm looking on the Subglacial hydrology. That's one of the key for explaining the seasonal evolution. I would say there for them, but there may be also some other stuff to look at, which for example, we have some people looking at Oslo in Svalbard, and what they see is suddenly, so the glaciers can accelerate and be very fast. And the process there is that, I mentioned that earlier in the trial lecture, is sometimes they are cold-based. So it means that they are sticking to the bed. It's frozen. But sometimes this cold can be removed, and suddenly it becomes temperate, which means you have water, and then you have this sliding. So it means that suddenly all the ice is gone. So that's another aspect that we mentioned today. What people are looking at otherwise, change, yeah. If we remain on, we can talk about maritime glacier. So there are these calving glaciers, but I'm not sure if we're going a bit far. Yeah, it's okay? With that? Okay.
So, because otherwise we'll really here for 6 hours.
Yeah.
And that is kind of my last question of this more big general questions, and then I will go back to Pete. If we have time enough, I might come back to that one, so you might come to remember, but maybe we'll see. But I state from your introduction chapter, there you write, your thesis contributed to our understanding of the effect of change in the subglacial hydrology on the response of the glacier bed. Now you did a lot of work, looked at a lot of different aspects, you tried many new techniques, but overall, what do you think are your two most important contributions to the field? If you have to name two of them.
It's this load transfer. Because it was quite funny, last June I went to a conference and in Iceland on glacier hydrology, and suddenly I end up with two guys they're getting quite, famous in glaciology, quite young, and they mentioned this anti-correlation. So suddenly, like for 20 years we have not, like in 1995 was one paper on this, in 2000 another one, a colleague of yours, and then nothing happened. We didn't observe this behavior. And suddenly, in the 2 years, people see this anti-correlation, and load transfer is there to explain this. But then and it was mentioned by one of these other guy that we have never talked really. So this load transfer is important for the propagation. So how do you suddenly have a one channel, but how come the whole glacier, which can be 1 kilometer wide, starts sliding when it's coming to this tiny channel that can be 1 meter, 1 meter wide? So that's one. Now, so this is not part of the thesis, but I've looked at these events. I've looked at, okay, I can maybe understand how are they caused. So we have this drop, but also this peak afterwards. And I realized at the end of my PhD that they are actually, so they are changing over time. I've shown you that. Every month they are changing. And it's an observation that I've never been done before. Usually they measure water pressure. Pete, they have these boreholes. They measure water pressure in there. And water pressure shows just these fluctuations. It doesn't show this drop and peak. And I think this drop and peak are containing much more information than just this water pressure in boreholes. So it's telling you not only the water itself, but whether you have channels. What is the size of the channels? And this is something that, as far as I know, you'll have to confirm me that nobody never was ever able to measure it, to give data. For example, I think that the peak, if we are right, with what we understand, the peak intensity will tell you how big were the channels, that were drained, and this drop tells you also a bit about this size. So that's something that needs a bit more work, but it can bring a lot to constrain, our understanding of this drainage system. So that's the two things.
So I've got a couple more broad questions before we sort of dig into the sort of few chapters. So I guess the first one, obviously you'll have to be diplomatic how you answer this, but when I was reading, I was thinking Gauss has already done a lot of great work on this data set up to the point. So what did you think were the key limitations that made you think there's still more to be done here in relation to the sensing work?
after my PhD.
No, in terms of Gout has already published.
Yeah.
He's already looked at loads of census data and published a couple of really
Yep.
nice papers. So in terms of what do you think are the organisations of those that require more analysis of?
So there was Gauto really uses so a part of the drainage system called the thin water film. So instead of having cavities, you have something maybe a millimeter thick water layer. And so Gauto used this as a base for understanding these sensors. So there was not. I think it might be. I don't know how true it is. I ended up following this at the beginning, and then I realized maybe it's actually more mechanical. I had the feeling that the ice itself, not only the water layer, would control the pressure. So then I looked at this mechanical aspect. So that's one thing that was not mentioned. I mean, they mentioned the stress bridging, but not this load transfer. One thing is with Gauto also, some of his work were split kind of really roughly. You have he looked at these events, but it was really like looking at each of them. So I'm sure it took a lot of time, and you get a sense of what it is. But to be able to explain it to people, you have to split it, and you split it in winter and summer regime. And I felt there was not this continuity, and that's where a continuity brings a bit more understanding. You can, and that's why I thought was a limitation of just single stuff. Because Gauto also found some anti-correlation events. I mean, I looked at Gauto's data, and these 2003 events, that was at the end of your PhD? Or some, no, yeah, in the middle. And so it's like the data were coming, but there was, some processes that we observed. We look at them, and I found them quite interesting and look at it a bit more. It's a lot of data, so he picked the most important bits, make it broad, and it's a very good paper. And then I try to, let's say, go in some directions that he promoted in a way, like this, very nice correlation between sensors. What would I? Otherwise, yeah, it's very punctual. Yeah, I try to bring this continuity, I would say.
In terms of the sort of the wider relevance, clearly, it certainly looks as though in the brain, certainly where you are, it's hard-bedded. How does what you looked at compare or have relevance, do you think, to sort of soft-bedded?
So that's what's for so what happens? So when you have a soft bed, what's clear is the whole. You still have a drainage system. You still have channels. What may differ is that in these sediments, water can flow in the pore in between the sediments. So that's something about medium which is different. However, for example, this slow transfer was observed at another glacier called Trapridge Glacier in Yukon, and that was soft bed. And they observed this anti-correlation. In Greenland, so there's this paper from Lauren Andrews, published in Nature in 2014. They observed this anti-correlation, and I mean, it's Greenland. I mean, it's a mix of hard bed, soft bed. It's not sure what they had at the bed, but it could be soft sediments. So these observations of anti-correlation, this maybe load transfer, is applicable to these sediments. Stress bridging, maybe one thing is because you have this arching and the transfer of stresses, so you really increase the stresses on the side. It may help actually to deform more sediments. There's also this how does the channel changes over time. This shape changes over time when you have soft sediments. This can have an effect on the sediment deformation, and this maybe close faster the channel. So that's what we bring.
Okay. And then discharge?
Yeah. From the Lotzes,
Yeah.
it's about 500 meters, 600 meter. The furthest away is 800, less than a kilometer.
Yeah. And do you think that matters? In other words, obviously, one thing about the whole lab is it's amazing you can get access to the lead, but also it's clearly there as part of the subglacial water capture scheme. Is that? Do you think that's fundamentally affecting the pressure distributions and the water routing that might be relevant to where you're working?
To my data, I don't think so, but yeah, it definitely changes a lot. So these holes. So you have to think you have a big rock tunnel, and suddenly, I mean, in a way, you blast the bedrock where you know the glacier is not too far, and these holes are creating a big low pressure. And water under a glacier goes from high pressure, because it means the water is under big, thick ice, and it's going to go to this low pressure, these big holes. So what you may have is a funneling of the whole catchment in this area. So in a way, it's actually good, more good actually for the data, because it means that there is a channel more or less going to this intake every year, and the location is controlled. So it's not varying. And the good thing is it's downstream from the Lotzes. It's not upstream. Then you would reduce, you would shut down the drainage system. So then I would think it's actually, yeah, it's changing the dynamic. Jack Kohler looked at the effect of this, and he didn't find any strong effect on the glacier dynamics. So there is maybe some evidences that it's, I can't be 100% sure, but this doesn't have too much effect. So that would be what I would think. But it's definitely changing the way water flows.
Yeah, because I just wondered if it's such a big low pressure
Yeah.
that it's in a sense just sucking the water away.
Yeah.
That in fact you might be more isolated from a lot of the meltwater than otherwise, just because it's such a steep.
Although, yeah, the bedrock topography. So is actually quite. I mean, you end up also in a place where you had a big plateau. If you look at the glacier, you had a big plateau, and it's actually going into a small, narrow valley. And in a way, I would expect this would create the same, funneling in a way. So due to the geometry, yeah, it would anyway do like this. I mean, the water would flow in the middle of the valley, I would think.
Okay, great. So let's dig it down into the.
Yeah. 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 What was the page already? Page 38. In the paper. Yeah, okay. We're gonna do it differently. I can go to the table of contents. And what's happening? Wait a minute. That's one. It should be. Ah, yeah, okay. Stupid stuff. Up, here you go. Up, here you go. So we can go from there to this one. Yeah. I can make it bigger. I just need to change. Come on. Huh? Come on. It's locking it, yeah, but I can go there. 200? Yeah, here we go. So that's it.
What do you think is the real reason that this bottom set of sensors, which are only, they're only 45 centimetres apart, why are they so poorly? I mean, they're correlated up to a point, but given how close they are, it seems amazing.
So yeah.
They're not almost perfectly coloured, even in winter. So I mean, it's a fascinating data set.
Yeah. So I looked at those ones, I presented those ones, that's the easiest to understand. Now we start to those ones, which are actually, so they're on a kind of a flat area, and they are 45 centimeter apart. And I did the same work here. So you still see an increase in correlation, but actually it does not reach 1, although they are 45 centimeter apart. And so and the variability is much greater. So what I think is happening is we have parts of the glacier bed that are more likely to have water, and some more likely to be isolated. The question is why this part would be more active. What would be more, there is two possibilities. Because it's a bit more flatter, and you have a cliff on one of the sides, maybe it's bringing more water in this area for some reasons. I don't have the knowledge of the bedrock topography further upstream, but maybe there is some topography that makes the water flow more preferential over these two lotses. And when the water is on one, as you show, you have a channel, you can have a completely different response, even at 45 centimeter apart. Because it's known that when you have two boreholes, two water pressure, they can have a very, very strong gradient, so showing the very different response. So I would think that somehow it's passing over one and not the other. It's the only way. It's like active, and they are on an active part of the bed with water that is flowing over preferential pathways. That's the only way I could explain it. Unless you have another idea. I don't know.
I just wonder whether one gets, I don't know, more sediment flowing over it, or I mean, it just seems amazing that something that is so close.
Yeah.
So poorly.
Mm.
I mean, it clearly is.
Yeah, and I can, I showed at some point at the end this closure, and one load cell is showing, let's say 2 megapascal, the other one is 1 megapascal. As if suddenly half the glacier was gone. And so I think rocks could be, at some points in time, there could be that some local conditions are blocking in between them, but it's really a flat area. Is it coming from the instruments? I don't think so, because Denis Cohen, more or less, it's a guy that also worked at the lab in from 98 to 2006, and later actually, and he found the same. That's there was like one of his sensors had much more pressure than the other, even though they are like 45 centimeter apart, something like that. And the only way you could find is that there is some local conditions above or upstream or rock that is causing this. That's why it's local overburden pressure what they are measuring. It's never overburden pressure.
So what are the implications of those results for trying to average and then potentially model, take shear stress, basic pressure, whatever, and often with modelling you're trying to average and yet this is showing extreme
That's what.
system on this kind of scale.
So that's the problem, in that I wanted to find some implications for the whole glacier range, and that's why I got stuck, because I could just say, okay, if you look at the whole glacier beds, the whole glacier, maybe the bedrock topography has a lot of importance, on a very small scale, and somehow you have areas which are more like these ones, and areas that are more like this one. So where you have water, you are more likely to have this, and if you have very little meltwater coming, then you are more likely to have this. So it could actually potentially say that this upstream, like in the accumulation area where you have less meltwater, you would have this, whereas in the lower part, it's more like that.
Okay, and then if you go sort of down to the
Yeah.
to the file, just across to the and then
Oh yeah. Okay. Yeah.
so what I was going to come on to now after this is the sort of detailed data from 2000
Three.
from 2000
2000. Yeah.
2003.
Yeah.
And so, as we'll see, and as you've already shown, they're pretty amazing data sets, one very positively correlated and one with the anti-correlation. But when you look at 20 years of data, they're like sort of unique, I mean, they're almost one-offs. That's the really positive bit. And then this is the anti-correlation bit. So, of course, we all choose the sort of most exciting end members to look at, but they actually look like quite rare.
And that's yeah.
In relation to the overall data.
And again, I think we are looking at small scale. So we are looking, do we have a channel beside the load cells? So I felt that the load cells were more like, imagine that you have a weather station on a glacier, and you have a storm coming. You know, you place your measurements, your station at one location, and at some point you have a storm coming, so you measure something, you measure the storm weather, but sometimes you don't have the weather storm coming. So in a way, what I felt is we have a passive sensor that sometimes we are lucky enough to measure these processes. So because of the variability, the way it flows, so I feel that it's times where we're lucky to measure one system, and in my mind it was like, this should happen much more, but we are not lucky to have a channel measured by the load cells. I mean, the channel is maybe 1 meter wide. Do you have the luck that it goes over the load cells? For these ones, it may be that the channels was at the right locations and affecting all the load cells. And the question is, you know, every year the meteorology, the melt is changing, so it's.
Because overall, if you just looked at that over 20 years, you'd sort of, with a couple of exceptions, you'd say, okay, it's not that well correlated. It's all behaving rather uniquely.
Not if you look at LC4. This is for sure. If you look at LC4, you can see that there is a pattern, and every summer you have an increasing correlation.
That's the one that's 1 meter away.
Yeah. But what I didn't do is, for example, doing the correlation with the reference, because so these two load cells are a bump. They have a bump in between compared to the rest. So maybe this bump has some effect. And what I didn't do is, for example, looking at this as a reference, and then maybe this would actually be more correlated than with the other sensors, because there might be a bedrock topography, again affecting this, and other thing is this is showing monthly correlation, and it tends towards no correlation, because sometimes you have no anti-correlation, sometimes you have correlation, and if you do the mean, you have zero, although you have actually a strong signal. So what I did is, when I did the mean, actually I could see this pattern, correlation pattern, more or less. So it doesn't mean then they behave all the same, but there is something every summer coming, I would say. But this is monthly, so I know, for example, you don't see this anti-correlation so well. 2002, 2003, that's the blue here. If your signal is not long enough, you don't see it there. And it may depend on how do you measure that, the correlation window, for example.
So if we keep on 2003, but go to the 2 pages later, so on page 40 of the paper.
Mm.
Yeah, so that right-hand one. I mean, it's fine at that.
Yeah?
Yeah, that's fine. So in the paper you talk about this
Yeah.
being driven by the increasing discharge signal.
Yeah.
Which I think all that makes total sense. But in terms of I'm surprised it's not in some of the other, because that that increase in discharge in sort of May, June, July, or sort of May, June, it might be shifted a few weeks and the amplitude might vary a little bit. But the basic spring melt pattern is kind of replicated. So again, I'm sort of intrigued that it wasn't more prevalent in other years.
So what I did is I really looked at every year. I didn't look at all only these two. And I tried to, again, try to do what you're doing now is trying to say, okay, I should see it somewhere else. I should see it in other years. And for example, for this one, I realized actually 2008 has also a kind of strong correlation pattern. And if you look at the discharge, it's more or less flat. For this one, I see periods that are also anticorrelated, but never such a long one. For this spring melt, I mean, spring melt for me is here. It's actually May. Yeah, it's here. The spring speed up event is here. So for me, that's the melt period. This is some. I mean, it's related to. It's not related to that. I mean, directly. I think we are talking about the development of the drainage system and what you have. And this is a bit later. So what is here is a very rare phenomena where somehow this temperature was more or less rising, like there is this drop, but stable increase in melt, and somehow they must, yeah. And this is rare. It's not, fluctuating so much. So somehow there is something continuous.
And you don't see that in other years, that sort of gradual.
No. But for rainfall events, I see it. But then it's, it's a few days, it's a week. If you're lucky, this is let's see, one rainfall event here, and then like two couples once there. That creates the peaks. But so that's why it's actually a long period. But then if I look at the data again, I can see a peak. An anti-correlation for one event.
And is there any velocity data? Because I think in the conclusion, if you write about the difference between 2000 and 2003, there's a perfect comparison there to see whether, with what in Britain you think 2003, it must be going quicker, if your interpretation is correct.
And just maybe explain why I'm laughing is because Alexander Messeli spent a PhD trying to get this surface data, this velocity data, but everything failed. No? No? Well, we did not everything. It's true. We got one spring event. But so looking at the archive, so is the archive? Is there other data from this? So Miriam will confirm me. There is some data in published 2010. There is data in 2011. 10 is published with Pitmore. Other than that, there is Jack Kohler that measured some data in 95, 97. So not exactly those years.
What I wonder is just in relation to really sort of, I'd say, confirm what you found. And I know it's not your expertise, although you could but find somebody who can process Landsat or something.
So that's the other problem. Yeah, we did have some thoughts like. But Engabrienne is a very maritime glacier with a lot of clouds. So the issue is that, it can be tough to find Landsat imagery, Landsat satellite imagery to actually do this velocity. So Alex found some good periods. Since we have the new Landsat, now it's much easier because it's much more frequent. They're taking images much more often. But before, it's quite tough. I know that there is also some radar measurements, but that I've not looked at. So, but there may be some problem of, it's a maritime glacier, which means for the radar, if you change the surface condition, so when it's maritime, suddenly you're very dry, it's very, let's say very dry, and at some point you have a storm, and you're so close to the sea that suddenly it becomes wet. And if you have an image before and after, you can't measure surface velocity. So, because you lose the coherence, it's not the same surface structure that you observe. So that's another problem with radar and Engabrienne. The problem is the maritime climate. That's it. Hopefully, yeah. I would.
Get Maria or someone to chuck a GPS on, so 2 years' time when you get that, you can
Yeah.
get two perfectly contrasted years,
Yes.
and then you can
Mm.
and then you have another nice paper.
I would. Yeah. So there are some challenges, because it's highly crevassed. But you know, there are areas that I would be interested actually to put GPS upstream than the lab. You know, there are parts which are not too crevassed, and one downstream, so you get an idea of the timing, and so maybe you can. That's the way I would do it. And then I think there's the possibility with the satellite archive. You never know. Maybe at some point there is some spy satellite that you know. Suddenly we have a lot of data from them, and they release it after 40 years maybe. So and I've not looked at all the data, satellite data. So there is maybe some that could be used, but I don't know. But I would preferentially throw Alex and put some GPSs on the glacier.
Okay. So then just one more question, and then I'll move on to the regular. So on the sort of paper 2, so the sort of second paper in the appendix, you don't need to bring it up. It was just to say, in terms of, I wonder if you could expand on the sort of wider implications of those results. Because again, it's a sort of a narrow area, both in terms of the field data, but also the numerical model. So you're looking at a sort of a small spatial extent for obvious reasons, but how do you upscale that? How does that become sort of relevant to even at the regular grain? What do you think, how regular do you think channels are? How do you change the sort of detailed focus?
Yeah. So what so there's been a bit more understanding since I tried to publish this paper. So this paper looks at the model. We have problems with the boundary conditions. So you change the size of your domain, the height of your domain, you get completely different result. So what it says is that it's really going to change with the glacier shape, the bedrock shape. So actually it seems that you have to do it case by case. So that's one problem with this upscaling of load transfer. But what I observed is that it can give you an idea of this peak in anti-correlation. You know, what is the place where you still have you have a reduction of the load, and so you may have more sliding in these areas because you reduce the friction. So I don't know the feedback there. It looks like there would be some feedback happening, but I would say it gives you an idea of how far can the channel affect the ice, and so then you should actually look at the surface velocity for a glacier. And then you should see, okay, I have boreholes that are showing anti-correlation, anti-correlation, and then it stops there. And hopefully it would show that it's the size, the width of the acceleration, let's say. So that's where I would think maybe this load transfer could say that's how far the glacier will accelerate. Because we see bounds, like in Greenland. But it may be controlled by the bedrock. Yeah.
There he sees a regular change in pressure.
Yeah.
But also if you look at sort of surface velocity profiles, they tend to be smooth. So it's that they're integrating this sort of stress bridging.
Stress bridging or load transfer? Yeah.
Or the sort of load transfer. In other words, do you think you've got lots of these sort of mini sort of areas of load transfer, which are then just, because you're saying you look for differences in
Okay.
velocity,
Yeah.
but
Yeah.
you don't see these at the...
Yeah. So there is one problem with load transfer is in the paper we say that because of the lateral condition, it means that the way to create this anticorrelation is that you have one channel here, and then a bit further you have another one. That was the only way to create so load transfer. It means that you have both channels that must be flowing parallel, suddenly both at the same time increase pressure, in water pressure, and then can lift up, take the loads of the ice in between. I have a bit more understanding since then. It's like due to the lateral condition, boundary condition of this model, it can also mean that you have just a cliff, so rock, and so somehow the load would, get a grip, or like would be helped by this wall, and it would put the pressure on the wall and would reduce the pressure at the base. So that's another way of interpreting the lateral boundary conditions. So it doesn't mean that you have only channels, two channels of this, but it could be like we have this cliff, because I think again when you look at what we know from the bedrock topography is that you have the load cells, one cliff, load cells, maybe a step, and then a tall cliff. From what I heard, when the people were melting, so this cliff could also be another reason. This stuff from Lauren Andrews, it seems that they're in a particular location of Greenland, where they had actually they were upstream. Somehow the bedrock topography was weird. They didn't realize when they drilled, but it could be that they have a bump and these boreholes are downstream of the bump, and so maybe actually the load transfer is, using this bump. And if you look at Murray and Clark's 1995, she observed that they had like 3-4 boreholes, and they observed that they had 2 channels, and in the middle this anticorrelated pressure signal. So it's like they have, let's say they have more sensors, but let's say they have 3 sensors, and 2 were measuring water pressure, and then for that it was channel, and in between you had this anticorrelated pressure. So, okay, I didn't lose track a bit, but it's showing that it should be happening. It should have implications. I'm not sure how far. I've never quantified anything. And we don't have surface velocity, so I can't really extrapolate further than that. But it seems we have this either double channels or compression regime, because you need compression. That's maybe in simple words, you need 2 stuff compressing, and you do an arc in a way, and then it reduces and it takes more load on this arc, and it reduces pressure below. So maybe you can quantify, that's the idea would be to quantify what is the reduction in friction, and maybe you could link it with the surface velocity. But I've never came up with an answer.
No, I mean, it's very hard. I just wondered, down the line, if you were working more with Olivier or something, what channel spacing would be most important for amplifying most motion, or
I didn't think of that, but yeah, that can be done. But then what we saw in this paper is that if channels are very close to each other, you have a much greater anticorrelation, so a much greater reduction in friction, and so the glacier should flow faster. So close channels, I mean, that's what I tried to come out to as it's one of the results. If you have channels that are very narrow, very short spacing, they will create this stronger anticorrelation. But what we realize is even if you look at 200 or like a spacing of 400 meters between 2 channels, you still have an anticorrelation.
I would like to stay a bit with paper 2, and then I come back to the question that actually but we don't need the pages.
Okay.
You use finite element modeling
Yes.
in your second paper.
Yeah.
And I would like to know why you actually use that modeling approach, and
Yeah.
if you could give me some advantages, disadvantages of using this approach.
Okay.
as opposed to other possible.
Yes. So, okay, we have to talk about load transfer stress bridging. And it means that you have stresses transferring from one node to the other. And finite, and you need to solve, so, and it, so these stresses depend on the ice flow. That's also an important bit. And the ice flow, you have different models to that you can use, and different assumptions. Different assumption that can reduce an equation called the Navier-Stokes equation. And this Navier-Stokes equation, it's the only one, if you consider it, it's the only one that solves the whole stresses problem. So the three-dimensional, and that's, so why, and the only way to solve this equation in the 3D aspect is the finite element model. The problem with this, it's highly, it's computationally expensive. You need a very, very powerful computer, but then you get the exact result of this equation, whereas other models use assumptions. What I can add is we need it 3D. You know, if you look at a bridge, if you're looking at 2D, if you were looking at 2D, if you look at the bridge, the part in the middle, like between two pillars, would fall down because it does not transfer the stresses to the pillars. So that's one problem. This stress bridging and load transfer would never occur if you don't account for all this stress tensor.
Then the next question touches actually both papers and goes also back to what you already started to discuss with Pete. You even state in the conclusions of your paper, you kind of highlight again these extreme gradients in the pressure between load cells that are so close, and we have already discussed quite a deal about why this could be and what could have been the effects on the two load cells to make them behave differently. But my question is more, and that's again kind of getting a bit away from your load cells, a bit out. Are there any other possibilities, maybe other type of measurements that you could link your data to? And now we have heard about velocity. That's a difficult one, obviously.
Yeah.
But I mean, just elaborate a bit on that.
So
what possibilities would there be?
to measure pressure or to measure subglacial changes?
No, to find explanation why these load cells show such extreme gradients in such a short spatial
Okay.
area.
And then would you have access to the bed, or you just have access from the surface? Okay. What I really like in the literature is when you start to have this grid, a grid of sensors. It's really, I felt it's the only way to go if you want to understand these processes. Because hopefully, yeah. So one way would be to do like boreholes. So from the glacier surface, we drill again, and we reach the beds, and we measure the height of the water in this borehole, gives us pressure. And there's some very interesting papers on this, and I think it's those ones that really make the difference. So that would be one way to explain the gradient, because there is a paper from Hubbard, and you are on it? No. In 1996, just after Murray and Clark. And so what they really have, it's a very nice data set, they have 30 boreholes. And actually they don't see the load transfer. They see something a bit different. They see that it's actually, when the water pressure is high in the channel, they see a decrease in pressure away from it. And so it means that the water goes from the channel to the sides. The other thing is, sometimes you have a decrease in water pressure in the channel and the high pressure on the side. So it means that the water goes into the channel. But I talked to Christian Schoof, which is a highly, very good mathematician, very good in theory. He told me that he could explain this behavior by a load transfer thing. Okay, so there is this problem of, you know, Herbert's, this paper is the only one that showed this kind of, as far as I know, it's the only paper that showed this gradient, and this is due to conductivity. Okay, so there's boreholes, grid of boreholes. Maybe, you know, you can say, is it conductivity or is it load transfer that can exist? So that would be one way. The other way, for me, is to use more a grid again of pressure sensors. Because, I mean, we have 2 sensors, but imagine that you have 6 or 9 of them. Then you will have actually the 3D geometry of your channel, and you could prove that it's a narrow thing. If you don't have pressure sensors, I don't know if it's possible, but I thought about it. I think it could be, is that you place some very small temperature sensor. And if they're small, you can put like tens of them. And then if you have water, the temperature may rise a bit. So then you may be able to say there is water. And then maybe you see actually how does the water flow as the temperature gradient changes. So that would be a way, like 3 ways to measure that.
Yeah, I especially want to give the downhole measurements.
Yeah.
That's fine. One moment.
Yeah.
Okay, so just one last question on
Yeah.
that. So if you have got these high stress regimes on the side of the channel, in principle they'd be isolated. How do you get water into channels if you've got a nice big, in effect, hydraulic dam or stress bridge all the way?
That's right, you don't have it.
Right.
That's why it's the problem is this paper that if it was not existing, I would have I would say that the water does not go into the channel. It's not drained in a way. There is this isolated drainage system, and then the water would stay there. Yeah. So in a way, if we would block in some areas, you know, it's stress bridging occurs in one particular case is when the channel is more or less at atmospheric pressure, so that it's not filled with water, or it starts the water level starts to decrease, and that's actually a particular case. So when suddenly the whole drainage system drains and the water goes away, but you may have this system where you have water pressure that is, you know, not at flotation level, but a bit below, and this actually still may happen. So this conductivity and exchange with the distributed drainage system. So stress bridging is for one particular condition, low pressure channels, more or less. If you don't have that, you can exchange water. Shall I go? Do you need more?
Not sure I agree, but it's fine.
Because what would be?
Well, no, because I just think at low pressure, I mean, even from dye tracing, you know, you chuck, it all ends up in the same channel.
Yeah, but you know what? Yeah.
To be able to get water into a channel somehow, whether it's low pressure, high.
I have a lot of questions about dye tracing, because I'm not sure I do believe it so much. When having Thomas Schuler here, where he showed like so many times that you have so many different factors changing, you know, the behavior of the dye in the subliminal trace system. Maybe the much more interesting is American at UNIS, Jason Gully. That showed that actually the same dye tracing return that you showed at Glacier, he showed the same shape, but they knew that they only had one channel, and but it's just the roughness of the channel that may change. So that's why dye tracing, you know, you also maybe the main problem with dye tracing is that you either need a Mullen where you already have a connection, something happening. If you do it in the borehole, there is always this problem that the dye stays at the bottom. So I think you already have a connection if you do dye tracing, and that is the problem. You don't measure these other parts; they isolate it, and you won't get any. I mean, if you don't see your dye return, I would expect. I mean, it would be normal, but then you would be disappointed because you don't get anything. So I would propose that you go to Gabriel and you put a date from the below. That would be the way to verify that.
Well, I will. Okay, so just the last couple of chapters. The chapter 5, which was the sort of the connect and SFM.
Yeah.
But it was really just what I say. You touched upon it. You said that it sort of didn't work. That was something you were going to put on.
Which chapter 5?
Yeah, I don't really need to.
Okay. Oh, sorry.
So that you open the cavity.
Yeah.
And then look in detail at the subglacial topography.
Yes. Yes.
And use structure, use all sorts of
Yeah.
clever techniques. So it seems pretty cool in terms of the technique. Why the aim of that actually was, because it seemed like you generated an amazing map of the very, very detailed.
Yeah.
Look on page 81, it shows the audience a map of
81?
Yeah.
Oh, you mean this?
So that, well, that would be.
Yeah.
So you've got that, beautiful map of the bedrock in terms of the sort of detail. I just wondered what the sort of real aim of that was.
I don't know. In my dream, I would have mapped all the beds to actually model the water flow, because the Gauta did some pump test experiments. So we can pump water from the bed, and I would be really interested to look at how does the water propagate. But I need a bedrock topography, and so the idea was to map the whole bed. But when you work at the lab, you can only map one area at a time, because if you make the too big cavity, it may collapse. But it's also just tough to measure it fast enough before the cavity closes. So the aim would have to full coverage, and what I realize now, the most important is the upstream part. That's what you need, because the downstream is not influencing too much. And for example, we have these two losses here, and we have this trough there, and I don't know how does it affect the pressure here, and how it would be. Water flow under a glacier, water can flow uphill. So that's a little step. You can just do it, but it's still may have some importance for the local scale and the way the pressure of the ice, affect this area. So that's actually, I think when we were melting the cavity, so we arrived from here and we were melting, and I thought at some point, I didn't take a picture, but I thought that I could see a cavity once here. And it would mean that actually, this is actually a low pressure area, and then you can actually attract water here. But it's not big enough. I can't really prove it. But if it would be big enough, I would also, be able to have a ice model and show how does the ice move over this area, and then be able to know where does the water flow. But it's not big enough. So no, it's feasible, but you need a lot of time and a lot of field work. And in the plans, we thought we could do it, and then we realized it takes a lot of time, and then reach the extent we wanted.
So is it sort of fair to say, as it is now, it's more of a demonstration of potential? It hasn't really sort of delivered results that we plan to use?
No. All, yeah.
Okay, then I pull it up here. Yes, since I'm dealing with remote sensing in my daily life now, rather than with subsurface processes,
Yes.
I was of course very intrigued about the tetrapatogenic and
Yeah.
motion. So I read it and came to conclusions, and then of course I got a bit disappointed, but I think it's very, you outlined the problems very nicely, so I liked that very much, even though, of course, I would have liked to read this new method.
Yeah.
But you say that for several reasons, it's not possible to use the SFM model, which proves to be kind of be the better one. Let's say for erosion studies. So at the moment, so what is the main limitation at the moment, and how would you overcome it if you could continue this type of work?
So structure for motion is again taking pictures, creating a 3D model. The problem is you need to reference this model, and I tried actually. So what we did, yeah, you can just explain. So what we did, we drilled actually a reference system. We drilled it at different places, and we placed and we measured this system on the bedrock. The problem is I measured this system in a not so nice way. So I thought, okay, if you want to have a reference and ground control points, you can do triangulation. So what I did is, which was not clear at the time, is we don't have too much space. So what I did is I screwed some ice screw in the ice at 3 locations. And then I measured the distance between this ice screw and each of the reference points. So I had for the other part, I had 21 ground control points, and multiplied by 3 is the number of distance measurements. So the problem is I didn't measure the distance between the points on the bed. So I cannot constrain properly this data set to obtain ground control points, exact positions. But it's something super easy that you can come back, you can melt again, and you'd use a laser, and yet you get it correctly. So that can be done pretty easily. There was another part of the question.
Yeah, the question would then be what needs to be done to use the model for erosion studies?
Yes.
Is it just kind of
Yeah.
the correct triangulation, or would you need more?
So the erosion is so as we talked about erosion rates, and it's a question of millimeter per year, and sometimes even hundredth of millimeter. What I think that some areas can be used from the data I have. The problem is you need to have to take, so the SFM, the resolution of the DM depends on how far you take pictures from the surface. So honestly, it's not easy to take pictures in these wet environments. We have rocks, pebbles, stones falling on us. We have the mud. It's cold, wet. And sometimes when you look at the pictures, it's a bit blur. So one thing would be to take better pictures, take closer, and then we would obtain the resolution we want to measure erosion rates. And if we have the right reference system, we can then do this mapping 10 years later, and then look at, do you have these grooves maybe that we observe?
Okay. With this, I would like to start with chapter 6, and then it will go up.
Yep.
That's the one where you create your own ice cavity.
Yes.
On figure 6.2, I think.
Yeah.
Well, first of all, just total out of interest.
Yeah.
How much time does it normally take you to unfree the load cells? That has nothing with this cavity to do now. But
Yeah.
when you come out of the magic door and meet the ice wall.
Okay.
How many hours does it take before you can start?
It depends on your hot water drilling system. It used to be much better, but nowadays, to reach, let's say, the 2 load cells that we've seen before,
because they're about 20 meters from the door, aren't they?
yeah. More or less, we start melting at 6 in the evening, then we melt until 2, and then we start again at 6, and usually before midday. So 6, 12 hours, a bit more.
That was just
Yeah.
pure curiosity. But then when you have this, okay, the figure 6.
But that's the first load cell, huh?
Yeah, that's a figure 6 too, where you created your own
Yeah.
cavity. It seems to have a peculiar form.
Yes.
And so I was wondering, how did you, first of all, kind of And is there an optimal geometry for such an experiment? And then also kind of why is it having this, yeah, rather peculiar form
There.
at the right edge? Yes.
So yeah. So let's say this cave here.
I might say that's like maybe cave 2 is the one that kind of looks non-peculiar to me.
Yeah.
The one looks a bit.
Yeah. So this was the cave 2. The shape was more or less melted overnight, and you don't work too long sometimes. So we have like a fireman, thing where we spray water, quite a big volume, and sometimes we leave it on a tripod. And this cavity, no, it's cavity 1. So cavity 1 was left overnight and melted the cavity a shape like kind of weird shape, more or less. But it was more or less that. And then we started again in the morning, and I was like, shit, that's not good. So then we did like really firemen and having it, on the shoulder, and then we tried to melt. Because actually, if you look at the beginning, when we melted it, it looked quite nice. Actually, it looked quite like that. But so that's because we did manual melting, because we wanted to have a nice shape. What the problem is also here, sometimes you have fractures and then water flows behind and then flows, so it melts much more at the bed. So I would say you need to be there all the time. If you need to have a nice shape, you need to have it on your shoulder and then nicely follow the shape you want it. And that's what we did with cave 2. So, yeah.
So last couple of questions on this. So one of the things that in modelling is that the importance of the value of n, and that you said that some of the characters there were also Cohen suggested that n here actually might equal 1. So how transferable is that? Is that just a local quantity? Because if it's not, what are the implications for modelling?
I think that n equal 1 is actually very true for the lower part of the glacier. So it may not extend to the whole column. So just for those who don't know, n is, so it's a relationship between the deformation rate, so the deformation of the ice, the flow, and then we have a constant, more or less, and then it's related to the stresses at the power n. But this power n varies between 1 and 3, and even 4. 3 is usually the one mostly used, and the problem is here, to reproduce the data that we have, n equal 1 seems to be the best. It has been shown that n equal 1 when you have a lot of sediments in the ice. So n equal 1 means the ice is softer, or at least at the beginning, for short stress scale. And this softness can be increased because you have sediments, and that's what we have. Can I show you something? Do you have the video? It's here. So come back. We can talk about it if we go to. We have a video of the ice closure, so maybe you can we can talk about it and see how soft is the ice. It's just quite interesting. But to continue, n equal 1 is. So there are ways of looking at, the property of the ice. This n equal 1 depends on the property of the ice, and it can be that so the sediments make it softer, create this. And that would be the reason. So okay, that's one cavity. So you see the scallops is due to the melting, and then you have here the bedrock. Our stuff is on it, and then here you have sediments, and that's another view. On the other side, you have clear ice, sediments. The door, famous door, is just behind here, and that's a video. If you look at here, you see the ice deforming. So what we did is we left the camera under the ice. It took a picture every minute for 13 hours. Well, if the frame is moving, is because the ice decided to move the camera to flow faster near the camera, something that we didn't expect. But it really shows that in some areas, you know, for some reasons, you may have a softer ice, and so maybe an equal one is more justified. If I can do it again. So here you have deformation, look like a toothpaste, and here you are actually sliding. So you see this part here is just sliding over the bedrock. And you see it's rotating. There is some very interesting motion in this one. But that is due to, yeah. Yeah, okay, we talk about, yeah, yeah.
You should make the modelling community as it made clearer to the modelling community, because people still tend to use N=3 when they're doing their modelling experiments of channel growth and breadth.
Yes.
If N=1 is
I think, yes, yeah.
number, then that's actually really important.
Yeah. Yeah. It's yeah. I would agree with that. That yeah, it's every time you model channel. I mean, you focus on the interface between the ice and the bed, and that you model something there. N=1 is maybe most likely. And then, then if you model the whole glacier, I think you don't need to have N=1. But it may be still, you know, N=3 if you don't have so much sediments. That's another thing. So it's something they should try, at least. They should model with N=1 and N=3 and see what's happening. What's the difference? They should show that. For sure.
Approaching the final part.
Yeah.
One of the hours is also approaching, so
yeah.
I will finish up with some broader questions again.
Okay.
And yeah, you did 4 years of intense work, a lot of hours in this cavern.
Yes.
Making these just by looking at it. A lot of work in front of the computer, modeling. We already talked a bit what you see as your two major contributions, but every upside has a downside. So I would also like to hear a bit, what do you consider maybe as the weakest part of your work, or you can also phrase it or look at it from a different angle. Looking back, what would you potentially do different if you start again?
I would do everything different. Because if you look at I felt that during my PhD everything is like rushing up, so you go to the next stuff, and then you realize, oh, you know, for the modeling I needed this value, so I needed to do the experiment different. But what I really realized is every time you do field work, it's the best to do the modeling before, because you know what do you need to actually you have understood a bit with the modeling what is controlling what, and what you need to measure to verify your model. So you know, okay, I should measure that and that and that. So for example, I think for the closure experiment, there is not enough constraint. And that's why we do a very simple geometry, modeling of a simple geometry. I would have started doing also this, you know, this, yeah, load cells analysis, this time series. I would have started with it much faster. It's something that I did a bit at the end. And I would have actually looked at the events. So I talked about these pressure events. I would have talked about it first. Then I would have gone to the season and load I would have everything together in a way, because what I realized, this load transfer tells you what you're measuring, because it tells you we are not measuring water pressure in an efficient drainage system. We are measuring this isolated drainage system, and that's an output that I didn't put in the paper. This justification, we measure the isolated drainage system. And that's what these events are telling me now. How does this isolated drainage system behaves? So yeah, the weakest point is in the is the wrong order. Everything is in the wrong order. I would have published something before. I would have published 1 year instead of 20 years. That because the paper that I published is a bit complex, and I mean my English is correct, but getting it understandable may be problematic. So I don't know if everyone understands what the output of this paper. So I would start with the modeling and with ideas, developing more strategy and long term, because I felt I was like falling into something, and then okay, I need to do it. Okay, I do it, but there was not this nice link that I made at the end. Somehow you managed to put the puzzle back, but it would have helped the understanding if it had been much more structured at the beginning.
That leads over to my next question. If you now would have the chance and he says, well, we have this poster position building up on your work, and we would like to have you for this task. What would be the next work steps you would do? What would be the next experiment? And maybe also what question
the problem with the network, the sensor network, it's deteriorating. And so why did I look at 2003? Is because it's when all the sensors were working, and working pretty alright. And nowadays we have only 4 more or less working, more or less. And so that's the problem. You need more of them working. You need the whole network to be up and running.
money would not be an issue.
Yeah. So that's what I assumed. So I would actually also start with a new type of sensor, trying to be smaller, to have many more of them. But usually they place sensors, they were placed at these locations for a particular reason. It's like when they drilled this long tunnel at the beginning, they had they wanted to check, where is the ice. So they were from the tunnel, they were drilling until they were reaching the ice, and we used these ones to transfer the cable down. So I would imagine myself just drilling loads of holes to have loads of sensors all over. A bit. So that's one thing. If this is not possible, the other way would be to have these temperature sensors. There are some that are buttons, and then you can drill a small hole, not put them straight on the ice because they may be destroyed by the ice, but a bit of cement or like some wire, then you would have that. That would be the grid that we mentioned. The other thing would be in Greenland, there's a lot of fun about lake drainage. So lake drainage, you have the ice sheet is melting. You have this lake that form at the surface, and suddenly they drain. And it has been shown that the ice accelerates, slides more. What people don't know is how does the ice propagate at the bed. And I think we have this pump test that Gaute did, and I think we could have loads of these small pressure sensors around where we inject the water, and we could see the pattern, the way the water flows, because some of the model assumes a perfect like a bubble. So you reach the bed, it creates a bubble, it grows, and then it flows, create the channels. And I think we can confirm this model by doing it at the lab. Because the cool stuff at the lab is really cool. Is you can have a karcher, this karcher to clean terrace, and we plug it to this. And that was the coolest thing I've done. Is that I lifted the glacier with a karcher, because the karcher has a pressure higher than the ice, and so it's really funny. The karcher injects water into a rock borehole, and then it reaches the ice. What happens is it builds up pressure into this rock borehole. And then at some point when you reach the overburden pressure, the water is gone. And this is something, you hear it. It's quite funny. You hear the karcher reacting to the water leaving and to the lifting of the ice. And so by mixing this karcher and this small maybe temperature or pressure sensors, you can form a 3D model of how the water flows at the bed. So that's grids. I like grids. I think it's the way to go. You get a 3D image of what you can observe. Then the dye would be a cool stuff to do, but I don't know the implications. I would not. I think it's not just an idea. Cool stuff to try. But yeah, it needs more holes to have more sensors.
Okay, fine. We just wrote your research plan. So
Yeah,
let's
yeah,
design
yeah.
as you like.
Yeah.
I would like to end with my last question. I had the pleasure to meet John Rödensberger sometimes when
Yeah.
I came to coffee at ETH. I was too young to have been sitting in his lectures, but he was often a guest at the coffee table, and I followed his discussions in awe between him and Urs Fischer and
Okay.
others. Unfortunately, he passed away, but if he would be here today among us and would still be doing research, how would your work influence or maybe even change his work?
Mm.
Or in other words, are there any textbooks that have to be rewritten now?
Yes. So Rossi's special work. I mean, one of his most important pieces in glaciology is that he found the equations to develop these channels that we observed. He found a way to have a steady state, and so the problem, yeah, for him it would be fine actually. It's more like big names like Nye, Nye who actually also looked at these channels, because Nye assumed that there is no stress breaching. So people are still using this equation to model. So Rossi's pressure would be fine actually. It's more Nye, and this was already discussed by Wirtman a bit later, saying with what Herbert mentioned, we have this problem. How does the water flow away from channels and in channels? And in some conditions, you may have a sealing effect. But that's already mentioned by Gaute, so it's not really my work. Although we bring a step further to prove that it's happening. Then yeah, it's. I think the problem is if we had surface velocity measurements, we would have rewritten some bits, I think, but we don't. Sorry. The parts of maybe one of the main output is I see papers that have just one borehole, and they assume that the whole glacier bed measure. They measure the whole conditions of the bed, and I know Dogben, I think, has been two boreholes in Chronobrian. Yeah, only one. Yeah, so there's this paper, for example. I don't want to be two boreholes. I don't want to be a reviewer for that one because I don't know if it will be a representative, giving a representative idea of what's happening at the glacier bed. I would say be a bit more careful. But what I feel is we need this subglacial data for the future, for the models that are developing. So, no, I'm not sure I will bring a huge stone to the work because it needs a bit more, that's what you gave me in the feedback for my thesis, is that the implications, there's maybe a step, to reach the implications to then reach, that we change a bit the idea. We are close, but there is either some lack of data, no offense. There is we have loads of data, but sometimes you need one tiny extra one that will confirm yes or no, this is this process. So that's what I would say.
Fair enough. Thank you very much.
Thanks.
So I guess it's just one last one, which I think is the hardest actually. Nice to get that answer. But as I said at the beginning, you've got this amazing data in an area about the size of this room, and we want to understand the behaviour of the green ice sheet, the West Antarctic ice sheet, how can we use your data to help inform modelers to upscale to these big
Um, so, as we mentioned, these mechanical processes, I think, can have an effect. And one way to simulate kind of or parameterize stress bridging would be that you have a threshold. So you have a subglacial hydrological model, and if the water pressure is getting lower and lower, at some point you may have a small you could reduce the flow of water into channels. So there may be a way of parameterizing so that on the side of the channel suddenly the conductivity or the connectivity is reduced because of stress bridging. So that would be one way to simulate this stress bridging effect. This load transfer, you would need a finite element model, but that may be possible with element ice. But all the other models, I don't know how you would be able to parameterize it. So that's the issue. Concerning the connectivity, as you said, it's a small scale. I don't see myself being able to extrapolate for the whole glacier bed, unless in this area, like in 2000, all the sensors were measuring the same response, and then I think, yeah, we have actually a broad scale idea of the glacier bed response. So then I would extrapolate. The way to help people in Greenland would be that we have actually borehole measurements and then water pressure. Because that's the whole problematic here. We're using a completely other sensors that completely measures a completely new system or different system. And if we had water pressure, we would be able to link it to the rest of the literature, which is mainly based on this water pressure from boreholes. That would be the way to the step further. But yeah, load stress bridging, changing connectivity, and load transfer. Maybe it's already it's already included in ELMA. That's so maybe actually you may see it already in some like Mauro's Werner's model. Maybe actually they will see it occurring. I don't know. That's the way.
Okay, thank you very much to opponents, both to Reidar and to Arthur. I think I don't think you have been sleeping much tonight. Now it's possible to speak extra editorial if anyone has any questions to Finn. I just wanted to clarify on the velocity field front. I think Finn is talking actually of resolution. So our biggest problem was that at the glacier surface, directly above the lab, I mean, Tim has measurement frequency at the low times of 15 minutes.
Yes, yes.
And actually what you need corresponding to the surface is something along that resolution, at least sub-daily. And GPS measurements in an ice fall are not really possible. So I think that's one of the biggest limitations. But at the beginning of the project was very idealized and would have been a perfect matching between the two surface and facial measurements. But the resolution is something.
Yeah, we need GPSs. We need like minutes, or that's the problem of the processes we're looking at. When you look at models, they models years, hundreds of years, thousands of years. And here we are looking at minutes. All these events occur in a day, but the changes are in minutes. And why minutes? It's because water flow changes are in minutes. The way water flows is very fast. So yeah, GPSs, I think we can still put some, where there is no icefall above or around, and maybe try to interpolate. That would be the way to go.
What will happen now then is that, I hereby declare that this proceeding are concluded, and a report will be made to the Faculty of Mathematics and Natural Science. And what will happen now is that the committee will go out and we will discuss a bit from